So students, there are some technical issues. Sorry for that. Let us resume our class. So the topic we are doing is dipole in uniform external field E. I have put this dipole plus Q minus Q, this pair in electric field, this direction of electric field, and force on the charge plus Q is plus QE, and force on minus Q charge is minus QE. So here the direction of force is in the minus negative E direction, and this is the direction of positive, and this is the direction of negative E. So that's the direction of the force, minus QE, and this direction, positive direction of electric field. So this will form a couple equal and opposite forces. So net force is 0, but they are not, they are along the different lines of action. So that is why it forms a couple, and a torque will act on it, and the torque, the magnitude of the torque is given by force, one of the forces, into the distance between the forces, so perpendicular distance between them, and that is, so here this angle is theta, this angle is also theta, corresponding angles, and this opposite side is hypotenuse sine theta. So same here, a sine theta is 2a sine theta. So magnitude of the torque is 2q a sine theta. Now, what is the direction of torque? Torque is a vector quantity. What is the direction of torque? So direction of the torque will be given by right hand thumb rule. Curl your fingers in the direction of the rotation motion. So obviously the force acting on this direction, so it will move upwards from this side and it will move downwards from this side. So it is anti-clockwise rotation. So curl your fingers of right hand in anti-clockwise and put them on this figure, and your thumb will tell you the direction of the torque. So your thumb is towards you. So the direction of the torque is perpendicular to the plane of the paper coming out of it. So you need to write, so torque, the direction of torque is normal to the plane of the paper, normal to the plane of the paper coming out of it. So students, whether it is derivation or whether it is numerical, if you are writing vector quantity, you need to write its magnitude and then you need to write the direction. So now torque is written as torque equals to PQE, P cross E. We can write it as, so torque is, so how do we write it? Now let us see how torque can be written as P cross E. So what is the magnitude of P cross E? The magnitude of P cross E is equals to magnitude of P into magnitude of E. So this QA is P, dipole moment. So P is equals to Q into 2A. So that is, this is P, and this E, and this sine theta. So, and look, if this vector A, this vector B, so this theta, so A cross B is equals to magnitude of A, magnitude of B, and this the normal vector perpendicular to the plane containing A and B. So here also it is the same case, that the direction of this torque is perpendicular to this plane coming out of it. So P cross A, E is the same thing, and so P sine theta, and direction of P cross E is also, you can see, where is P in the figure? It is from negative to positive charge. So this is your P And now where is the E? This is the direction of E. So this direction of E here. So this P and this E. So again, put your right hand on P and move it towards E. So put your fingers of right hand on E, P here. Put your right hand over here, P, and then curl the fingers in the direction of theta. So towards E. So P cross E. So from P to E. And again you will see that the thumb is coming out of the plane of the paper. So the direction of P cross E is same as the direction of the torque. So direction is same here. So P sine theta and direction of P cross E is, so the resultant will be vector, and the direction is normal, same as this, normal to the plane of the paper coming out of it. So therefore I can write, so this I can say from equation 1 and this equation 2. So from first and second I can write torque as E cross E. So what this torque is going to do, this is very important. This torque is actually, it will align the dipole with the field E, and when P is aligned with E, so this when the dipole will reach here, this Q plus Q and this is minus Q. So this is the direction of dipole moment, and that is the direction of electric field. So the angle between them is 0. So you can see clearly here that tau is equals to, in this case, PE sine 0, and that is equals to 0. So the tau is equals to 0 and there will be no torque. Now the question comes here is, what if the field is not uniform? So this field is not uniform. So in exams, question asked up to this point, you need to derive this relation. Tau is equals to P cross E, and another question that is tagged to it is about the equilibrium, stable equilibrium and unstable equilibrium, and that is there in chapter 2 also. So in chapter 2 we have, when we will finding the potential energy of the dipole in the external field, so at that point of time we will write about the stable and unstable equilibrium. So this is the potential energy. It will be written as minus P dot E. So this will be doing in chapter 2, and tau is equals to P cross E. This is what we have done doing right now, chapter 1. So we'll do it, the energy, and then discuss about stable and unstable equilibrium. But for now, we have tau equals to P cross E, and we are discussing the case when the E is non-uniform. See, when is E uniform? That's another important. See, we have these two plates. There is positive charge on this plate and there is negative charge on this plate, and electric field lines will be from positive to negative. So this is the case where field is uniform. So where electric field is uniform anywhere over here. So this is the example of electric field between the plates. This is the example of uniform electric field. So if the field is not uniform, then so obviously if the field is not uniform, the force will not be zero. This force, this electric field is something else, this electric field is different, so these two are different, so net force will not be zero. So means net force will not be zero. So still there will be torque on the system, and we'll consider a simple case when P is parallel to E or P is anti-parallel to E. So when P is parallel to E and P is anti-parallel to E. So in the book it is written, they are written horizontally, which is figure 1.23. So now net force is non-zero. So definitely there is net force on the dipole. So you can clearly see that this is the direction of E, and we have this dipole over here. This is minus Q, this is plus Q, and this is the direction of increasing field. So field is increasing in this direction. So the field is increasing in this direction. So obviously here the field is lesser, here the field is more, and that is why F is equal to QE and F is equal to Q something E. So E, you know that E is equals to F by Q. So Newton per Coulomb. So suppose E here is, for example, 2 Newton per Coulomb. So here the E is increasing. So it can be 3, 4, 5 Newton per Coulomb. So force electric field is increasing. So let us assume that here if it is 2 Newton per Coulomb, it is 5 Newton per Coulomb. So field is increasing. So 3 Newton per Coulomb and 5 Newton per Coulomb. So that is why the net force is not zero. So now the force on plus Q will be given by F is equals to plus Q into E. So force on plus charge is always in the direction of electric field, you can see. So that's the force acting on plus Q charge in this direction, force on plus Q. And what about minus Q? F equals to force on the minus Q. So here this if I'm writing E, so here I can't write E because otherwise it will be uniform. So the force definitely, if it is minus Q, so it will be in this direction, because you know the formula that F is equals to minus QE, so negative direction. So force on plus charge is always in the direction of electric field, and force on negative charge is always opposite to the electric field. Why it is so? Electric field starts from positive charge outward. So if you put a positive charge here, so it will be repelled by this positive charge. And if you put negative, so it will be attracted towards it. So if electric field is entering the negative charge and you put plus Q, again plus Q will move in the direction of electric field. And if you put minus Q, this will be repelled. So it will move against the electric field. So logically also in both the cases, so minus Q will move against the direction of the electric field. So that's the direction, that's the force acting on in this direction. So obviously you can tell me that if Q is same, then the force here is F is equals to the magnitude of the force is Q into this is 3, and here the force is equals to Q into E is increasing, so it is 5 here. So you tell me that there is 3Q Newton acting in this direction and 5Q Newton acting in this direction. So where will be the direction of the net force? Obviously this is the direction of the net force, that is 2Q. So this is the direction of net force, right? And suppose second example, if E is anti-parallel to, if P, so here the direction was P, this was direction of P, so P and E were parallel. Now let us take an example where P and E are anti-parallel. So let me switch all these charges, so this plus Q and this minus Q, and students, so obviously this direction from positive negative, this direction of the dipole moment. So now direction of electric field, obviously this is the direction of electric field. So now this is the direction of increasing electric field. So here the electric field we have written was 5 Newton per Coulomb increasing, and here the field was 3 Newton per Coulomb. So that was the magnitude of electric field over here. And so I'm just assuming. So what is the force over here? So force on plus Q will act in the direction of electric field, and here negative. So force will act against the direction of electric. So how much is the force acting on plus Q in this direction? So the force will be Q, magnitude is Q into 3, and here the force is equals to, the magnitude will be Q into 5. So this force is more. So what direction of net force? So this is the direction of net force in this direction. So this happens. So it will move linearly in this direction. This dipole will move linearly in this direction, and here this dipole will move linearly in this direction, in the direction of the net force. So here the net force is in the direction of when P is parallel to E. So direction of net force is in the direction of electric field, and when the P and E are anti-parallel, then the direction of electric field is, then the direction of the net force will be in the decreasing direction of electric field. Okay, good. So now we have charge distributions. I will not go into the depth of it, but let me discuss about the charge densities. So when I talk about the linear charge density, I know the formula of mass density, that is equals to mass upon volume, and I also know number density. So number density is equals to number divided by volume. So here it is charge density and linear charge. So obviously this will be equals to, so this is the linear charge density. It is denoted by lambda, and this is the length, so linear line. So charge is along a line. So linear charge density is normally of a line charge. So line charge means wire. So this. So for wire, linear charge density lambda can be defined as delta Q by delta L. So for small charge, small delta L, and if there is uniform distribution, then I can also write it as Q by L. Now the second is surface charge density. So student, surface charge density is for the surface. So I have a plane sheet, and if so I want to find out at particular here on the charge sheet at particular area. So that will be given by the charge in that area divided by the area. So delta S is surface area. So you can write here A also. For the surface, it is surface area. And if it is uniform, then I can write it as Q by A or Q by S. That's the same thing. And the third is volume charge density. So volume charge density is given by symbol rho, and that is equals to, so volume charge density is about, this is a solid sphere, and if there is uniform contribution of the charge, obviously the charge will reside on the surface. So this will be given as volume charge density, or simply you can also call charge density also. In the similar way, we will write it delta Q by delta V, and if it is uniformly charged distribution, then I can write it as Q by V. So this was about the charge density. So charge upon length for linear charge density, because wire has length and surface charge has area, so surface charge density, so total charge on the surface divided by total surface, and volume charge density, total charge divided by total volume. So now our next topic is Gus Law. So all this surface charge density will be used when we'll do the applications of Gus Law. So now let us first understand what the Gus Law is. Gus Law relates the net flux of an electric field through a closed surface and Gaussian surface. So net flux of electric field through this Gaussian surface divided by the net charge enclosed by that surface. So the electric flux is equals to Q by epsilon naught. So this is the Q charge enclosed by this surface. So this is the Gaussian surface, and charge here enclosed in the surface. So if it is suppose plus 2 coulomb, it is 3 plus 3 plus 4 coulomb, and here it can be minus 5 coulomb. So the net charge, so the Q enclosed will be written as plus 2 plus 3. So additivity of the charges, that property is studied, and this is 9 minus 5, and that is equals to plus 4 coulomb. So that's the charge enclosed. Epsilon naught, permittivity of free space, and electric flux is through the closed surface. So this is through the closed surface. So here we are taking all the charges enclosed. So En. So this is Gus law. So flux through the surface, closed surface, is equals to the charge enclosed. So already we have studied by definition that phi is equals to, in case of sphere, we can write it as E dot S. So that's by definition, and delta phi is equals to E dot delta S. So that is for the small flux. So here we can use this formula. So we need to have two conditions. First is E is supposed to be uniform and angle between the surface E and S is same throughout the surface. So same angle, same theta throughout. So if these two conditions are there, then you can use this formula, then you can write this formula. Otherwise you need to integrate. You need to put the sign of integrate. S E dot ds to the closed surface. Okay, but if you have E uniform and E and S are in same direction, you can use this formula. There's no problem with it, because if E is uniform, same theta, E is uniform, E is constant, E can be taken outside, and ds, I can write the integration of the total surface. So that is it. Let us prove the Gus theorem. So let us consider total flux through a sphere of radius. So I have proof of Gus theorem. So these were the definitions that we were discussing. Okay, so this is Gus law and I am writing the proof of Gus law. So this was something about the definitions. Another formula of phi we were discussing. So definition of the flux we were discussing, that we did yesterday. So let us do the proof of this. So obviously you need to bring the phi over here. So from where we will bring phi? You will bring phi from the definition, right? So the case that we have is that we have considered a sphere. Let us do the proof over here. So we have considered a sphere, and this sphere has radius r. So r is the radius of the sphere, and total flux through this sphere we are going to find, and this whole sphere is enclosing a point charge q at the center of the sphere. Now we will divide the sphere into small areas using this formula delta q. So this is one of those small area. So the flux through this surface area delta x, let us write. So flux through delta s is given as delta phi equals to E dot delta s. This by definition of flux. So this by definition of the flux, and this can be written as, so what is the electric field at this point? So the radius is r, distance is r, so E is equals to k q divided by r square. So the magnitude of E into the magnitude of delta s. So obviously the magnitude will be delta s, and then the angle between E and QS. So what direction of E? So direction of E here is, suppose you put from plus Q, the field will be radially outward, or you can put plus 1 coulomb charge over, it will move away. So that's the direction of electric field. And what is the direction of this? It will also be perpendicular to it. So E and S are along the same direction. So the angle between them is 0. So here it will be cos 0. So this comes out to be, so kq r square into delta s. So now let us find the total flux, because this is what we need to find out, the total flux through the sphere. So students, this is what you need to bring on this side, and total flux on that side. So whenever you are doing the derivation, you already know the result, so bring the variables and you need to prove this result. So do the calculations accordingly, remove the variables which are not there in the results and bring the variables which are there in the result. So total flux through the sphere can be found by adding all this flux. So flux through all the different area elements. So flux can be written as summation all through all delta S A Q by R square, where what is K equals to, where K is the Coulomb's constant, 1 upon 4 pi epsilon naught. So KQ by R square into delta S. So that's cos theta equals to 1. So that was KQ by R square into delta S. So that was delta phi equals to. So putting the value of delta phi over here. So this is the total flux. So now the constant will come outside. So K is constant, Q is constant, distance also constant. For all delta S it's the same distance. And summation of delta S can be written as, you can write one more step, summation of delta S, and summation of delta S is the total surface area of the sphere. So what is total surface area? That is 4 pi R square is the total surface area of the sphere, and here R square will cancels out, and write the value of K also. So K is equals to 1 upon 4 pi epsilon naught, because you need to bring epsilon naught here, and you don't need K and 4 pi, so that is equals to Q into 4 pi. So 4 pi will be cancelled out. So hence the flux through the surface is equals to the charge enclosed divided by epsilon naught. So hence we have proved the Gas theorem. So now we have example 1.1. Let us use the definition of the electric flux and Gus law to do this numerical, which is example 1.11. So this example of non-uniform electric field. So we have this three-dimensional plane, and a box is placed over here. This is the box which is placed over here. So this box is a cube. So it's a cube, and its one side is A, and it is placed at distance A away from the origin. So this is a cube, all the sides are A. So I have drawn it in 2D, but this figure 1.27 is there in your book, and it's 3D figure, you can clearly see it. Now so E is varying. So how E is varying? So along the x-axis E is varying as alpha x 1 by 2. So alpha root x, and that is equal, so alpha is given here 800 Newton per Coulomb. So that is the, so put the value of alpha, and that is the how the field is varying. So obviously if you are increasing x, electric field is increasing. So now we need to calculate the flux through the cube. So first thing, we need to find out the flux through the cube. And the second thing we need to find out is, student, this is very important question. Many times it has been in the board exams, and it is quite easy. So you need to find the charge within the cube. So charge within the cube and flux through the cube. And you need to assume here that the side, this A, is also given to you, and it is 0.1 meter. Now, electric field components are given in the figure, and you can see that this is one more important thing. This was the field in x direction. What about field in y and z direction? There is no electric field component in the y and z direction that is given to us. So no electric field component in the y direction and in the z direction, and that's equals to, so no component, so 0. Now we need to find here the net flux. So net flux will, so there is no field component y direction or z direction. So you know a cube has 6 faces, but only from 2 faces which are along the x-axis. From those 2 faces we will have the electric flux. So the total flux we know will be from the flux from the right face plus flux from the left face. So this is the right face, so this is the flux from the right face, and we have the flux from the left face. So that will be the total flux. So now, what will be the flux to the right face? So flux to the right face, you know the definition of the flux. So definition of the flux is given by E dot S. So here E, the electric field to the right surface, will be given by ER. So that's the magnitude to the right surface, and so E dot S. So throughout the surface field is same, so E is constant and the angle is also same. So we can use this formula over here, this one. So ER into field through the right face I am writing. So field through the right face, flux through the right face will be equal to field through the right face into, what is the area of the right face? So area of that surface is square, that is A square. And what is the angle between the surface? So angle, so the surface, direction of the surface is also perpendicular to the surface, that is the same. So the direction of, so the flux is coming out from this direction and to the right face. So this is left face and this is right face. So students, look, this is right face, this is right side, and this is left side. So to the right face, the electric field is in this direction. You can clearly see that it is it is increasing in this direction. So the electric field is in this direction. So this is the direction of electric field, and it is increasing electric field. So given by this formula. So direction of electric field and the direction of area vector both are same. So the cos here the angle is cos 0. Now the field is in this direction and the area vector of the left surface is this direction. So here, so in another case, so flux for the left face of the cube is given as electric field there, A square into cos, the angle is now 180 degree. So pretty simple. Now that is equals to, what is ER? So ER is alpha x1 by 2. So what is the location of ER? So I want to find out at this point. So that is equals to A and A, 2A distance. Yes. So here this x equals to 2A, right? So 800. So I'm writing ER, value of ER is equals to 800 into 2A 1 by 2 into A square, cos 0 is 1, so plus, what is EL? So so here x is equals to A, so x equals to A here. So the electric field will be 800 into A 1 by 2 into the surface area, which is A square. And what is the angle? Cos 80. So cos 80 is equals to -1. So that is equals to -1. So now we can just put the value of A and we can calculate the flux easily. So the flux, you can do these calculations and the flux comes out to be 1.05 Newton. So putting here A equals to 0.1. So putting A equals to 0.1, I get this flux as 0.5 Newton meter square per coulomb. Now the B part, so this was the A part. Now what is first part, you can say, and this is second part. So what is the charge through this cube? So students, see, charge, this formula now. So here we use the definition of the flux, and here I am using Gus Law. Gus Law states that this phi through the surface is equals to charge enclosed divided by epsilon naught. So we know this is 1.05. So what is Q enclosed? Is equals to phi epsilon naught, and that is equals to phi is 1.05 and epsilon naught is 8.854 into 10 to the power -12. So that comes out to be 9.27 into 10 to the power -12 coulomb. So students, look how simple these numericals are. The question was that Ex was given to you, and this is a varying non-uniform electric field. So at this, what is the field at this point? On the left, put x is equals to A over here. And what is the field over here? Put x equals to, so from the distance, the distance from the origin is 2A. So that's the position. So put x equals to 2A for the electric field on the right hand surface. So this is the only thing that you have done. So here you put x equals to 2A for the right hand surface, and here you put x equals to A, and then electric field into area and the angle between the area and the electric field. So, and you have found the total flux, because from rest of the four surfaces, up and the faces and down and towards you and away from you, from those four surfaces, the field is 0, so there is no flux. And now we need to find the charge enclosed. So how much is the charge enclosed? This is the charge enclosed. So we have charge enclosed in this formula of Gus Law. So students, quite simple example. Now we have one more example, that is 1.12. This is also quite similar example. So in this example, the electric field is uniform, and in what is the direction? Direction is positive x is in the positive x direction for positive x, and it is uniform with the same magnitude, but it is the negative x direction for the negative x. What does it mean? So look at the figure here. So this is plus x, and obviously this origin, it is minus x on this side, and this is y-axis, and I have this cylinder. So this is the cylinder. This figure 1.28 in your book, page 36. So now the electric field is uniform and in the positive x direction from positive x. So this is direction of electric field for this surface, and for negative x direction, this is again. So that is the direction of E. So that is then the positive direction, positive x, and uniform with the same magnitude. So magnitude is the same, so I can write E here because of the same magnitude. And it is given that E equals to 200 I cap Newton per Coulomb. So this is what electric field is given for x greater than 0, and E is equals to minus 200 I cap Newton per Coulomb for x less than 0. So this is the electric field for x greater than 0, and this is the electric field for x less than 0. But it is uniform at all the places because this constant, the direction is different only. So this I direction, this negative I direction. So a right circular cylinder of length 20 centimeter and radius 5 centimeter. So this is 20 centimeter total. So this length is 10 centimeter, and this is again 10 centimeter, and the radius is 5. So the radius is 5 centimeters, and has its center at the origin. So that's the center. That is why this 20 is taken, 10 on this side and 10 on this side. So this is x equals to plus 10, on this side x is equals to minus 10. So this x equals to plus 10 and minus 10. Now what we need to find? We need to find A part. What is the net outward flux through each flat face? So we have to find the flux through each face. So flat face. So we have only two flat faces. One is right, another one is left. So we have to find flux through the left face and then flux through the right face. This is what we need to find. Then we need to find B part, total flux through the side of the cylinder. Side means curved surface area. So flux through curved surface area. And then C part of the question, what is the net outward flux? So obviously net outward flux, you just need to add these three. So this is what you need to find. So that will be equals to phi L plus phi R plus phi through curved surface area. So that is the flux. And next D part is you need to find the net charge enclosed inside the cylinder. So students, this question, flux through the cube, yes, flux through the, so this is what you need to find. Here also you found flux through right surface, flux through left, so here you are finding them separately. So this is the same thing you are doing in both the questions. Look, the extra thing is, here you are finding CSA, there also you were finding, so this was CSA and there was theta was equals to even the E was 0, but here the angle between this curved surface, you can see the E is here and the curved surface will, the angle will always be 90 degree. So this flux is going to be 0 because theta is equals to, theta between the E and the surface vector is 90 degree. So this is 0. So same case as the example we have done above, but here the field was varying and here the field is uniform. And then we found the net charge, yes, same way by definition and then by using the Gus law. So both the questions, you can see the similarity in both the questions. So let us first start our solution of this numerical with A part as, so the A part we have to find phi L, and phi L is, by definition we know that phi is equals to E dot A. So what is E dot A here? So phi L is equals to, so E equals to, so E dot delta S, or you can say this is the surface we are taking, surface on the left hand side you are taking, so that is equals to, so what is electric field on the left hand surface? So this is the right hand surface, this is the left hand surface. So electric field on the left hand surface, so this is the electric field on the right hand surface, x greater than this is the field on the left hand surface. So that is equals to minus 200 I cap and dot, what is the surface area? Surface area is pi r square, so magnitude of E, magnitude of SL, so the, if I'm not writing it in, so simply it's okay if you don't write 200I, you can simply write the magnitude. So what is the magnitude? Magnitude is 200. So you can simply write the magnitude, that is 200, and then the surface area, that is, surface area is that is a circle, so surface area of circle is pi r square, so pi and r is in meters, SI units we will be using, so this is you can write it as pi r square, so pi and r is sorry, so you can just let me write it again. So there are some technical issues. So magnitude of electric field and magnitude of the surface area, that is pi r square, so pi into 0.05, so 0.05 meter whole square, and then what is the angle between them? So angle between E, so here E is negative, you can see negative I, so the angle between them is 0, because this direction of E in the negative I direction, so this direction of E, and here it is positive I, so this direction of, and this direction of SL, and this direction of right surface. So in both the cases the angle is 0, so this comes out to be 0.0 and cos 0, that is 1, and you calculate it and you will find it 1.57 Newton meter square Coulomb inverse. Now the B part, phi L, it will also be the same, no difference, because the magnitude of electric field is same, angle is also same, so you need not to calculate it, you can simply write 1.7. Now the C part is, you have to find the flux through curved surface area, and that is equals to, I have told you that the theta is through, so this curved surface area, so throughout this surface area the theta is 90 degree, so, and cos 90 is 0, so this will be 0. And then the D part, sum of all of them, so that is phi, so phi is equals to, adding all of them, so 2 into 1.57, and that comes out to be 3.14 Newton meter square Coulomb inverse. And what about E part? That is also, now you can use the Gus law to find the charge enclosed. So because you don't have charge, so students, remember, if electric field is given to you, use the definition, and if charge, then Gus law. So that's the thing you need to take care of. So phi definition E dot S, and Gus law, phi is equals to Q by epsilon naught. So if charge we want to talk about, then use the Gus law. If electric field, in terms of electric field you want to discuss flux, then use the definition. So these are the two things you need to keep in your mind in all the numericals, and numericals will be so easy for you. So now we need to find the charge enclosed, so obviously you need to write the Gus law, that phi through the surface is equals to charge enclosed through the surface divided by epsilon naught. So, and Q is equals to, so similarly we are doing this as so discussed earlier, so that is equals to epsilon naught phi, and that is equals to, so what is the value of epsilon naught? 8.854 into 10 raised to the power minus 12 into, what is phi? Phi we have calculated 3.14, so charge enclosed is equals to 2.78 into 10 raised to the power minus 11 Coulomb. So that's all for today, students. Tomorrow we'll do the applications of Gus law, and we'll also do the exercise questions and some CBSE board questions. So I hope you have learned a lot from today's class. Today there were some technical issues, so class started at 8:20, but tomorrow the class will resume at, I hope, at 8 p.m. Thank you so much. Oh, sorry, at 7 p.m. So class timings are 7 to 8 p.m. every day. Thank you so much for listening to me. See you tomorrow. Until then, goodbye. And don't forget to subscribe the channel. And if you like the lecture, then please click the like icon.